In this video, we're going to have some examples of finding and classifying discontinuities of rational functions. When I say classifying, remember from our first reading of the week that rational functions can have two types of discontinuities. They can have vertical asymptotes and point discontinuities. Point discontinuities are also sometimes referred to as a hole in the graph. So you've got an otherwise nice line and just one tiny little point is undefined. So those are the two types of discontinuities rational functions can have. Let's look at our first example. So as it says in the finding and classifying discontinuities reading, my first step is going to be to actually, I need to find them before I can classify them. You always find discontinuities of rational functions by setting the denominator equal to 0. Discontinuities of rational functions come whenever the function is undefined, which is at the same time when the denominator is 0. So I can factor this. That goes like x minus 5, x plus 2, which when I set x minus 5 equal to 0 and x plus 2 equal to 0, I get x equals 5 and x equals negative 2. Here are my two discontinuities for this particular function. So let's even write that down. I have discontinuities at x equals 5 and x equals negative 2. Now, if I want to know what type of discontinuity, I need to look back at the original function here. So I know how the denominator factors. That factors as x minus 5, x plus 2. I also want to factor the numerator, which will give me x minus 3, x minus 5. Notice that my numerator and my denominator have a common factor in them. They have a common factor of x minus 5. So if I cancel that out, I'm left with x minus 3 over x plus 2. So now this function is not exactly the same as this function. So I've got the function y equals x minus 3 over x plus 2. Everywhere they are both defined, they are exactly the same, but notice they do not have the same domain. This function, my second function, is defined at x equals 5, where the first function is not defined at x equals 5. The x minus 5 factor cancels out entirely from the denominator. And so I have a point discontinuity. At x equals 5. This function will look exactly like this function. The graph will be exactly the same, except this one will have a tiny little hole in it at 5. The fact that the factor x plus 2 did not cancel out means that there is a vertical asymptote at x equals negative 2. So I had two discontinuities and I've classified them. One was a point discontinuity, the other was a vertical asymptote. Let's do another example. I need to find and classify the discontinuities here. Now I know that this is going to mean that I'm going to just factor everything, so I'm going to do that all at once. The numerator factors as x plus 1, x minus 7. The denominator factors as x minus 7 squared. And so, if I want to try to, well, actually, first let's say that I have a discontinuity at x equals 7. When I set the denominator equal to 0, that is the one solution that this will give me. I have a discontinuity there. And now I want to try canceling to see if it's a point discontinuity or a vertical asymptote. When I simplify this as an algebraic expression and cancel out that x minus 7, I will get x plus 1 over x minus 7. X minus 7 is still a factor of the bottom. It's actually the entire bottom now. It did not cancel out entirely, and that means it's a vertical asymptote. It's only a point discontinuity if you can get it to cancel entirely out of the denominator. And let's do one more. I've got x plus 4 over x cubed plus 4x squared plus x plus 4. Now, I do want to remind you, you can only cancel something if it is a factor of the top and a factor of the bottom. This x plus 4, even though it might be super tempting to just cross that out and cross that out, this is not a factor of the bottom. You must factor the denominator before you can do any canceling. Excuse me. So, I'm going to come over to the side and factor out this denominator. Now, we could use our factoring tricks from factoring of polynomials. This is a cubic, so it's not as easy to factor. Well, you can't use the same techniques that you do on a quadratic, but I can factor this by grouping. If I pull everything I can out of the first group there, that'll be an x squared. And then I'll be left with x plus 4 on the inside. And while x and 4 don't have any common factors, well, any interesting common factors, but 1 is always a factor of everything. So if I have to pull out a factor, I can always pull out a 1. Now look that I have two groups, and x plus 4 is a factor of each group. So I've got x plus 4 times x squared plus 1. So, and since the top can't be factored at all, I now have everything completely factored. So I do have a discontinuity at x equals negative 4. And if I set this equal to 0, then and try to solve for x, I'll end up with an imaginary number, which means that there are no zeros of x squared plus 1 on the real number line, which is all I'm concerned about when I'm looking for discontinuities of a graph. So my only discontinuity is at x equals negative 4. If I cancel those, I end up with the function y equals 1 over x squared plus 1. And remember from our transformations of rational functions handout, that is the function, or that is one of the three functions that I told you needed to know what the graph looked like. I'm going to sketch a very rough picture of that graph. It's pretty flat most of the time. It's got this horizontal asymptote of y equals 0, but it does have a little bump in it right there. Now, I want this is the graph of, you know what, I'm going to call this h of x just so that it's different. So that'll be the graph of h. If I want to graph g, I know that when I canceled out this x plus 4 factor, I was left with a function that I know what it looks like. So I can sketch that as well. It is a lot easier doing this in pencil, but at -4, there's going to be a tiny little hole, and otherwise the graph is going to look exactly the same. Now this is a rough sketch, so it's hard to make it look exactly the same, but it is intended to be the exact same graph. The only difference is this tiny little hole, and that comes from this factor of x plus 4. So these are closely related functions. They're not exactly the same. That point discontinuity does make a difference, but knowing what this one looked like is enough so that I can exactly graph this one. All right, and that is it for this video.